Understanding the architecture of language models is essential to grasp how they can generate human like text. While the mathematical principles behind them can be complex, a high level understanding of their structure provides valuable insights into their capabilities. Modern large language models are built on a transformer architecture. This architecture extends previous techniques that successfully modeled vocabularies for natural language processing or NLP, enabling models to generate human like text. These transformer models are trained on vast amounts of text data. By training the relationships between words, they can predict sequence of text that sounds natural and coherent. With a large enough vocabulary, transform models can generate responses that are difficult to distinguish from handwritten content. There are different types of implementation of transformer models, each optimized for a specific task. The first one is BERT, or bidirectional encoder representations from transformers. Developed by Google, uses only an encoder block to understand the meaning of word and context. GPT, or generative pre-trained transformer developed by OpenAI, relies solely on decoder block to generate natural language text. Both models leverage the power of transformers, but they are designed for different purposes. One focuses on understanding languages and the other one on generating it. Tokenizations and embedding. The first step in training a transformer model is tokenization, breaking text into smaller components or tokens. While these tokens often represent words, they can also include partial words, punctuations, or entire phrases. Once tokenized, the model needs a way to understand the meaning of each token. This is where embeddings comes in. Embeddings are a multi-dimensional numeric representations of tokens. And instead of treating words as isolated entities, embeddings capture their semantic relationships, how words are relating in meanings. For example, the embedding for dog will be closer to a puppy than skateboard because the words share semantic connection. So what about vectors and semantic similarity? Each embedding is a vector, essentially a set of numbers that describe words' meaning in relation to others. These vectors exist in multidimensional space, where the directions and distance between them represent their relationships. To determine how similar two words are, models use a technique called cosine similarity. This measures whether two vectors point to the same direction or not. The more similar the direction, the closer the relationship. So, how transformers understand context? The encoder and decoder block in the transformer models rely on multiple layers, but one of the most critical components is attention layers. Self-attention allows the model to weigh the importance of each word in a sentence. And instead of treating words in isolation, the model understands their context based on their relationship to surrounding words. For example, the phrase, the bark of a tree, has different meanings than I heard a dog bark. Self attention enables the model to capture these distinctions. So, how language models generate text? In a decoder block, attention layer play a crucial role in predicting the next word in a sequence. Each time the model generates a new word, it evaluates all previous words and determines which one are most relevant in forming the coherent sentence. This process continues iteratively. Each predicted word influences the next, building the response on token at a time. So language models powered by transformer architecture revolutionized how AI understands and generates text. By leveraging embeddings, attention mechanism, and deep learning technique, they enable natural, meaningful, and context-aware communications. Understanding these fundamental concepts provides a solid foundation of exploring the capabilities of generative AI in its real-world application.